chord. So anyways, we have our roller coaster coming down, right? And we're trying to find out what's going on throughout. So one of the ways you want to approach these types of problems is ask yourself, what type of energy does it have at different points? And so we have our two types we've talked about, which is kinetic, 1/2 mv squared. The key variable here is velocity. So you want to ask yourself, is it moving? If it's moving, then that tells you that it has kinetic energy. Okay, and then you have your potential energy, which is mgh. The key variable there is h. So that means, is it above or below the ground? If it's above or below whatever you're calling the ground, the reference level, then it has some potential energy. So let's just kind of look at these. So the first question is asking, what's the energy at the top? So the energy at the top would be up here. Well, first of all, I said the velocity was 0, so it's not moving, so there's no kinetic. So all the energy at the top is going to be potential energy. So to find the energy at the top, we're just going to use UG equals mgh. So all the energy at the top is all potential energy. So we'll go ahead and solve that. So that's 2,000 times 50. Is that 980? Okay, so it has 980,000 joules of potential, but that's also the total energy. So that's all the energy because it's only potential at the top. How would it change if this was moving? It would have kinetic and potential. It would have both types of energies at the top. But in this case, it only has potential. All right, what about at the bottom? Well, E initial equals E final, right? So if it has 980,000 at the top, how much does it have at the bottom? 980,000, right? So it has the total everywhere. At A, at B, at D, and everywhere in between, it has 980,000. So the answer would simply be 980,000. So that's really just a conceptual question. That's everywhere. Well, at point C, how is it manifesting itself? What kind of energy is it at point B? All kinetic. Yeah, so up here was all potential, and it's all changing from potential, it's losing potential, gaining kinetic energy. And so at the bottom, all of the it's turned into 100% kinetic. Okay, so 1/2 mv squared equals 980,000 joules. Okay, do the math on that. 1/2, was it 2,000? V squared equals 980. Okay, so that'd be your velocity down there at the bottom. Okay, ready for D? So D is asking you what's the velocity at point D. So again, you're going to ask yourself, what kind of energy do I have at D? Do I have potential energy at D? Yeah. Yes. Okay, I'm above the ground, so I do have potential energy. Is the car still moving? Yes. So we have kinetic. So we have both types. So at point D, we have kinetic and we have potential energy. Both types. So E initial equals E final. Now what should I use for E initial? Should I use it right here at point B, or should I use right here at point A? Doesn't matter. Why doesn't it matter? Because it's the same, right? 980, 980. So it's the same here, here, everywhere has 980. Okay, so we'll just write 980. Once you know that number, you can kind of just stick with it all the way through. Equals E final. So again, our E final, we're looking at point D this time. So now it has both kinetic and potential. Okay, so you can just do the math here. 1/2 mv squared plus mgh 1/2 2000 v squared plus 2000 9.8 times 20. Now you can always do little mini checks on yourself at least. How should this V compared to this V? Should be smaller. Okay, so that's, at least make sure it makes some sense. What are you getting for the V here? $24.2, good. Now there's another way to solve this, letter D. Anyone see a different way to solve it? Yeah.
Just because like you have 2/5 of the height and like the set of proportion. Well, I tried that, but I didn't think the answer, so obviously it didn't work.
Okay. Other ways? Yeah?
I did like the force times the distance at that point to find work, and then that's for the kinetic energy, so that's equal to 1/2 mv squared.
Okay, and what did you use the force, which force did you use? Okay, and what distance did you use?
20.
And you got the same answer? I don't think so. You did something wrong.
Energy times 20.
Okay, so I don't know where you did something wrong. Here's the other way you can do it. And I think you're on the right track, but you wouldn't have used 20 meters for your height. So the other way that you could solve this problem,
Oh yeah, sorry.
the other way you could solve this problem is we could change our reference level. So rather than using the ground as our reference level, we could change it. And we could say, all right, I'm going to make my reference level right here. I'm going to make my reference level here. I'm going to call this my h equals 0. Okay? And if I make this my h equals 0, here's what happens. Way up here at the top, I still only have potential energy, UG. But down here at the bottom at point D, what kind of energy do I have down here? All kinetic, right? Because we're now calling this our ground state, our reference level. So here we'd have all 100% kinetic. So we're going to have our UG equal to KE here, changing the reference level. So when we do this, we'll go our MGH here equals 1/2 mv squared. Now the difference is, what am I going to use for my height? 30. Yeah, so we're going to use our height of 30 because if this is our 0 point, we're now going to use our new height of 30 meters. And if we use that new height of 30 meters, you should go through 9.8 times 30 equals 1/2 v squared. So, based on this problem, since we did all those baby steps, it's probably just as easy to do it the first way I did it. But if I just asked you for D, it's easier to just change your reference level and then go ahead and solve it like this, and it'll be a little bit more direct. You should get the same answer. Does someone want to verify that we're getting the same thing? What was it, 24.2? Yeah, 24.2. Okay, all right, let's try one more.